Video 17. Inverters. The inverter is an indispensable component of all electricity generating renewable energy systems. In this video, I'll discuss the type of inverters and the functions they provide. Types of inverters. Inverters come in three basic types: those designed for grid-connected systems, those made for off-grid systems, and those designed for grid-connected systems with battery backup. Grid-connected inverters. Today, the vast majority of renewable energy systems, both solar and wind electricity, are grid-connected. These systems require inverters that operate in sync with the utility grid. They produce electricity that is identical to that available on the grid. This type of electricity is known as grid-compatible sine wave AC electricity. Grid-connected inverters are also known as utility tie inverters. They convert DC electricity from the array in a PV system into AC electricity. Electricity then flows from the inverter to the breaker box and is then fed into active circuits, powering refrigerators, computers, so on. Surplus electricity is then back-fed onto the grid, running the electrical meter backward. Grid-tied inverters produce electricity that matches the grid both in frequency and voltage. To do this, these inverters monitor the voltage and frequency of the electricity on the utility lines. They then adjust their output so that it matches that available on the grid. That way, electricity that is fed from a PV system onto utility lines is identical to the electricity that utilities are transmitting to their customer. Grid-compatible inverters are equipped with anti-islanding protection, a feature that automatically disconnects the inverter from the grid in case of a loss of grid power. That is, grid-connected inverters are programmed to shut down if the grid goes down. The inverter stays off until service is restored. This feature protects utility workers from an electrical shock. The inverter shuts down entirely in case of blackouts because it requires grid connection to determine the frequency and voltage of the AC electricity it produces. Without the connection, the inverter can't operate. Grid-connected inverters also come with a fault condition reset, a sensor, and a switch that turns the inverter on when the grid is back up, or the inverter senses the proper voltage and frequency. To avoid losing power when the grid goes down, a homeowner can install a grid-connected system with battery backup. Although inverters in such systems disconnect from the utility during outages, they can draw electricity from the battery bank to supply active circuits. As noted in the previous videos, such systems are typically designed and wired to provide electricity only to essential circuits in a home or business. Grid-connected inverters also frequently contain LCD displays that provide information on the input voltage, the voltage of the electricity from the PV array, and the output voltage, the voltage of the AC electricity the inverter produces and delivers to the home and grid. They also display the current amps of the AC output. Grid-connected inverters operate with a fairly wide input range. The DC operating range of the SW series, for instance, ranges from 34 to 75 volt DC. off-grid inverters. Like grid-connected inverters, off-grid inverters convert DC electricity into AC and boost the voltage to 120 or 240 volts. Off-grid inverters also perform a number of other essential functions discussed here. If you are installing an off-grid system, be sure to listen to this section carefully. Battery-based inverters used in off-grid and grid-connected systems with battery backup typically contain battery chargers. Battery chargers charge battery from an external source, usually a genset in an off-grid system. A charge controller is a battery-based system which does charge batteries. However, its job is to charge batteries from the PV array, not a genset. A charge controller therefore receives DC electricity from a wind turbine or PV array, then sends it to the battery bank. The charge controller also prevents batteries from being overcharged. A battery charger in the inverter, on the other hand, converts AC from a genset and converts it to DC. It then feeds DC electricity to the batteries. In off-grid systems, battery charging gensets are used to restore battery charge after periods of deep discharge. This prolongs battery life and prevents irreparable damage to the plates. Battery chargers are also used during equalization. So this is a picture of a battery equalizer. High voltage disconnect. The high voltage disconnect is a sensor switch that terminates the flow of electricity from the genset when the batteries are charging and if the battery voltage is extremely low. High voltage protection therefore prevents overcharging, which can severely damage the lead plates in a batteries. It also protects the inverter from excessive battery voltage. Low voltage disconnect. The low voltage disconnect in an inverter monitors battery voltage at all times. When low battery voltage is detected, the inverter shuts off and often sounds an alarm. The flow of electricity from the batteries to the inverter stops. The inverter stays off until the batteries are recharged. Low voltage disconnect features are designed to protect batteries from very deep discharging. Although lead acid batteries are designed to withstand deep discharges, discharging batteries beyond the 80% mark causes irreparable damage to the lead plates in batteries and led to their early demise. Although complete system shutdown can be a nuisance, it is vital to the survival of a battery bank. Batteries can be recharged by a supplementary wind turbine or by a genset. Gensets may manually be started, although some inverter comes with sensor and a switch that activates the generator automatically when the low battery voltage is detected. The fossil fuel generator then recharges the batteries using the inverter's battery charger.